Hello. Good evening to all of you. Am I audible?
Yes, Prashant, you are.
Yeah. Okay. Yeah. Thank you. Okay. So, everyone, good evening to all of you. So, today's session is just about concept revision for the syllabus of Quiz-2 exam. Okay. So, it's a request to everyone. Please do not ask any questions from like activity, practice, or general doubts. Those kind of doubt we can take care of in upcoming session. In our session and in TA session as well. Okay. So, ma'am will mainly revise the concepts of quiz 2
Yeah,
in today's session. Yeah, ma'am. We
right.
can start.
Prashant, am I audible?
Yes, ma'am. You are
Okay,
audible.
right. Thank you, Prashant, and good evening, everybody. Uh, I am going to switch off my video because my internet connection is not very good. So I hope that's okay, Prashant.
Yes,
Uh,
ma'am. That will be okay. Yes, ma'am.
yeah,
No
because
problem.
I'm just going to switch off my video. Are you able to see my screen?
Yeah, ma'am, we can see.
Okay, right. Thank you. I'm switching off my video. Uh, okay, good evening, everyone. And today's session, as Prashant has said, would be a revision session on the concepts of probability. We'll start with permutation and combination, and we'll understand basic concepts of probability. And again, as Prashant said, please do not ask questions about any assignment, specific assignment question. But if you have any question at a conceptual level, please feel free to ask the same. You may use the chat box, or you can, since Prashant would be moderating, you could just tell him whenever you have a question. So let's get started. So the main agenda for today is we start with basic principles of counting. Then we'll look at what are permutations and combinations. And we'll spend some time in understanding how to apply this permutation and combination. Because repeatedly, what we get as feedback is people do not know when it is a permutation and when it is a combination. So we'll just spend some time to understand when would you look at it as a permutation and when would you look at it as a combination. Then we move on to probability. Again, we give the basic building blocks of probability, namely the random experiment, sample space, and events. Then we'll talk about the basic probabilities of probability. We'll introduce what is called the addition rule. We'll introduce the notion of mutually exclusive disjoint events, and then we'll go to conditional probability, and finally complete the session with Bayes theorem. If time permits, we'll introduce probability trees also, which is a very important and very convenient tool to compute probability. So let's get started. All of you are ready?
Yes, ma'am.
Yes, ma'am.
Okay, right, right. Thank you. So let's get started. So the first part is what we call the basic count rule of counting. And when we call the basic rule of counting, we introduced in the lectures two rules, which is one is the addition rule of counting and one is which is the multiplication rule of counting. Now, just to illustrate what is the addition rule of counting and multiplication rule of counting, you can just look at, suppose a person wants to choose a shirt or a pant, then I know that I can choose a shirt. I have about 3 shirts available to me. It is a yellow shirt, a orange shirt, and a green shirt. I have 2 pants, which is a black pant and a blue pant. I can choose a shirt in 3 ways. I can choose either a yellow or a orange or a green. I can choose a pant, either a black or a blue. So there are 3 ways of choosing a shirt. There are 3 options for me to choose a shirt, 2 options to choose me a pant, choose a pant. And if the problem is I can choose either a shirt or a pant, then the total number of options available to me is 3 or 2, and I can write it as 3 plus 2. So this is what I call the addition rule of counting. On the other hand, if the problem given to me is I have to choose a shirt and a pant. So again, I go back and I realize that there are 3 ways of choosing a shirt. For every shirt I choose, I could combine it with either a black pant or a blue pant. So you can see that if I choose a yellow shirt, I could either have a black pant or a blue pant, orange with a black or a blue, green with a black or a blue. So there are 3 ways of doing this. There are 2 ways of doing this. The total number of ways of choosing is 1, 2, 3, 4, 5, and 6. So the addition rule of counting states that if an action A can occur in N1 different ways, this was my shirt, and this could have occurred in 3 different ways. Choosing a pant B was a pant, and this occurred in N2. N2 was 2 different ways. The total number of ways of occurrence of the action shirt or pant was N1 plus N2, which is 3 plus 2, and I get a 5. On the other hand, if the action was A and B together, I have to choose a shirt and a pant. It was N1 into N2, which is 3 into 2, which is 6. So I can extend this multiplication rule of counting not only to 2 actions, I can extend it to R actions which are performed in a definite order. So there is N1 possibilities of performing the first, N2 second, NR, Rth. All of them together can be performed in N1 into multiplication by N2, so forth up to multiplication by NR. This is what is called the multiplication rule of counting. And this basic principle of counting sort of leads us to define what is called the factorial notation. Now, what is a factorial notation? So I know that if there are N1 ways of doing the first one, N2 ways of doing the second action, N3 ways of doing the third action, then N1 into N2 into N3 are the total number of ways of performing all the 3 actions together. So imagine I have N blocks. There are N ways I can fill in this block. Then once I fill in this block, I have N minus 1 ways of filling the second one, N minus 2 ways of filling the third one into 1. The multiplication of N into N minus 1 up to 1 is denoted by a factorial N or N factorial. For example, if N is equal to 5, I have the first block which can be filled in 5 ways, second in 4, third in 3, fourth in 2, and the fifth in 1. So this N factorial is going to be 5 into 4 into 3, 20 into 3, 60 into 2, 120. So N factorial or 5 factorial is equal to 120. By convention, 0 factorial equal to 1. Any questions so far on the basic principles of counting and the notion of factorial?
No, ma'am.
Okay.
No, ma'am.
Right.
No, ma'am.
So now we move on to why did we understand about this factorial notation and the basic principles of counting? Because a very important thing when we are entering into the domain of probability is to get a permutation and combination correct. Now, permutation is by definition an ordered arrangement. So what is very important in a permutation is an order and it's an arrangement of sum of all of the objects. So again, if I look at our objects, you can see that. So the first way is the number of possible permutations of R objects from a collection of N objects. So I'm taking R objects. The first one can be done in N way. The second can be done in N minus 1. The third in N minus 2. Similarly, the Rth object, it would be N minus R plus 1. The multiplication rule is added and I get N into N minus 1 into N minus R plus 1 is the possible ways of arranging R objects from a collection of N objects. Now, when I have this N into N minus 1 into up to n minus r plus 1. I multiply the numerator with n minus r factorial and denominator with n minus r factorial. Because if I multiply the numerator with n minus r factorial, the numerator and denominator by the same quantity, I see that by numerator is nothing but n factorial, the denominator is n minus r factorial. So the permutation of r objects from n distinct objects is given by n factorial by n minus r factorial. So this is the first formula that we derive, and this derivation of the permutation is used the multiplication law of counting. Special cases include NP0 since it's equal to 1, NP1 is n, and NPn is n factorial. Now, the way we look at is when I have NP0, there is only one ordered arrangement of no object. NP1, there are n ways of choosing one object from n objects. There are exactly n ways. And NPn, that is, you can arrange n distinct objects in n factorial way. That is also what we have seen when we define the factorial notation. Now, one key point that I need to remember here is I am assuming that my objects are distinct. So this distinct, n distinct objects is an important assumption I have here. Now, what happens when repetition is allowed? So in the first case, I did not allow repetition. What does that mean? Suppose I have filled up my first thing with n object. One of the n objects that is not available for me to fill up the second block. I can fill it up with only n minus 1. However, if repetition is allowed, then the first one can be filled in n ways. The second can be filled in n ways. The third can also be filled in n ways. The r also can be filled in n ways. So again, applying the multiplication rule, I get n into n into n into n, n multiplied r times, which is n to the power of r. So the first in n, second in n, rth in n, and this is denoted by n to the power of r. So when my n objects are distinct, repetition is allowed, I have NPR, which is n factorial by n minus r factorial. Repetition not allowed, I have n to the power of r. So far, so good? Yeah?
Yes, ma'am.
Yes, ma'am.
Right. Now the next thing is, so here I assume that these n were distinct. Now what happens when they are not distinct? So if in the permutation of n objects, the p of them are not distinct. So you will always have problems of this kind where I am asking it, I have statistics. So how many I have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So my n is equal to 10, but all of them are not distinct. How many are not distinct? I have 1s, 2s, 3s. So I have 3 s's, 1t, 2t, 3t. I have 3 t's. I have 2 i's. I have 1a, 1c. Stat. I have 2 i's. 1, 2, 3, 1, 2.
Yeah, ma'am.
Yeah.
I is equal to 2,
Yeah,
ma'am.
I
Yeah,
equal to 2.
yes.
Okay, right. So now problems of this kind. So whenever you are asked to compute the permutation, you need to check whether this number of objects is distinct or not distinct. That is the first thing that you need to understand from the problem. Now, when it is distinct, then I see whether repetition is allowed or repetition is not allowed. If repetition was allowed, it was NPR, otherwise n to the power of r. Now, when it is not distinct, again I have n. When p of them are of one kind, then what do? I assume that this p, I'll put it as one block. Okay, then I'll have n minus p, which is the other. So what is happening is this entire thing is going to be n factorial. But this P is always among themselves. I can arrange them in P factorial ways, and that is going to be the same. So if I'm having a red ball, red ball, red ball, okay, this is going to be the same as a red, red, red. Red 1, red 2, red 3, same as red 2, red 1, red 3. So these permutations I'll have to remove from my counting. Hence, I have it as n factorial by p factorial. I can extend the same thing to if I have p1 of one kind, p2 of other kind, it would be n factorial by p1 factorial, p2 factorial, pk factorial. So when objects are not distinct, it is going to be n factorial by p1 factorial, p2 factorial up to pk factorial. So many a time, this kind of a problem, you need to, when I am just asking what are the permutations of, say, able. Now, are the objects distinct here or not distinct? Able.
Distinct, ma'am.
Distinct, ma'am.
Distinct, ma'am.
Okay. But if I'm asking for, say, paper,
Not distinct.
not distinct.
Not
Okay.
distinct.
So in able, if I'm allowing, so if I am allowing from able, if I'm allowing you to form words, again, I'm saying meaningless words. Okay. I'm allowing you to have repetitions. Then what would be the number of ways you can do it with repetition?
4 factorial.
With repetition. 4-letter
4
words.
power
with
4.
repetition.
4 to the power 4.
4 power 4.
3-letter words.
4 power 3.
4 power 3. Okay. Without repetition, 4-letter words.
4
4
factorial.
4
factorial.
factorial.
Without repetition, 3-letter words. How many 3-letter words can I form without repetition?
4 into 3
4
into 2.
factorial.
4?
3 factorial.
3 factorial or 4 into 3?
4 factorial.
4 factorial or
4
4
factorial.
into 3?
And 4 into 3 into 2.
4 factorial by 1 factorial.
I'm asking 3-letter words from able. How many ways can I do that?
Ma'am, 4 into 3.
4
It's going to be
factorial
4
by 1
into 3,
into
which
3
is
into
nothing
2.
but 4 into 3 into 2. Why will it be 2? Will it be 4 into 3 into 2 or 4 into 3? The first
into
one,
into 2.
not 3-letter words. First can be in 4 ways, second can be in 2 ways, third can be in 2 ways, right? 4, it's 4p3, which is 4 factorial by 1. 4. Is that right?
Yes, ma'am.
Yes,
4
ma'am.
factorial.
Okay,
Yes,
so
ma'am.
it's the same as 4 factorial. Okay, right?
Yes, ma'am.
Okay, so the first thing you need to understand is whether the objects are distinct, whether they are not distinct, whether they are repetitive, whether they are not repetitive. That is the first thing that you need to understand. Okay. So now the next thing is this, all the things that we saw so far were what we refer to as a linear permutation. In other words, I'm arranging these objects in a line. Okay, so you will find that most of the problems that you will come is, okay, how many ways can I arrange 25 people if girls are sitting together and boys are sitting together? Couples, where couples sit together. All problems of this kind, you can apply this. When people are people distinct or not distinct?
Distinct.
Number
Yes.
of
Not distinct.
people are not distinct, right? But
Yes.
when I want two of them to sit together, when a couple has to sit together, you know how to arrange them. Is that clear?
Yes, ma'am.
Yeah, right. Now, the next thing is, many a time will say, okay, I want to arrange people in a table, or I want to arrange beads in a garland. I want to arrange balls in a circle. All problems of this kind where my arrangement is not linear, but it is what I refer to as a circular permutation. In a circular permutation, what happens is, in a linear permutation, when I had A, B, C, D, how many ways could I arrange A, B, C, D?
4 factorial.
How many ways could we have
4
arranged?
factorial.
Repetition allowed or not?
How many ways could I arrange A, B, C, D? I'm not choosing.
N minus 1 factorial.
4 factorial.
4
If it's a
factorial.
linear, it would be first one can be A, second can be B, C, D, or it could be A, B, D, C, and this way it is 4. First way can be any one of the 4, Second could be any one of the three, right? Because there are not repetition not allowed, it is 4 factorial. Is that right?
Yes.
Yeah. So now what I can do is, if I fix A and I turn it into a circle, this is a line, I'm making it into a circle. I am fixing one of the things. What is the number of ways I can arrange the other 3? If I fix one,
3 factorial.
it would be 3 factorial.
3 factorial.
Agreed? Okay. So now
Yes, ma'am.
this A, B, C, D is one arrangement in a particular direction. In the other direction, it could be A, B, C, D also, right? These two are same. A, B is next to C is next to B. These two in a circular way, whether I start in this direction or this direction, they are the same. Agreed?
Yes, ma'am.
Right? So if they are the same, so when I talk about a circular permutation, again, there are 2 ways to look at a circular permutation. The first idea that I have in a circular permutation is I'm fixing one of the objects and arranging the other. So that is what I mean. I know in a linear, it is n factorial. If I fix one of the objects, it is going to be n minus 1 factorial. But however, in a circular permutation, the direction matters, whether it is clockwise or whether it is anti-clockwise. Till here, is it clear?
Yes, ma'am.
Yeah.
Yes,
So if
ma'am.
the clockwise and anti-clockwise are different, then this ABCD is different from ABDC. I'll have to count each one of them differently. Okay. Similarly, ACDB is same as ACDB, is different. ADBC is different from ADBC here. So these are different. So 1, 2, 3, 4, 5, 6, which is 3 factorial, which is 6 ways. However, if they are the same, then what would I do? If they are the same, then how many, what if that clockwise and anti-clockwise are the same, then what would be the number of permutations? This is the
Ma'am,
same as
divide
this.
by 2. 6
I divided by 2.
2.
So when I talk about a circular permutation, I need to understand that there are 2 things in a circular permutation. It could be, I need to see whether clockwise and anti-clockwise are same, or whether clockwise and anti-clockwise are different. If they are same, it is n minus 1 factorial by 2. If they are different, it is n minus 1 factorial. Now, within the circular permutation, then I can have all other things. See, this is the basic case, right? Now, within this, I could have, okay, 2 people always want to sit together. Then what would happen? Suppose I had 5 people to be arranged in a circle where I have these 2 people who always want to sit together. Then how many ways can I arrange them? And
3 factorial.
Because I will consider, is it only 3 factorial?
Yes, ma'am.
Why? What are the assumptions you have there?
Ma'am, we
2
will
factorial.
both
2
those
factorial.
people as a
3
same.
Okay, you
factorial
tell
into
me
2.
first 5 people in a line where 2 people always have to sit together. A, B, C, D, E. How many ways can I arrange them in a line where B and C always want to sit together?
4
4
factorial.
factorial.
Is it just 4 factorial?
Yes, ma'am.
Is B, C sitting together the same as C, B?
No, ma'am.
So what would be the number of ways?
Factorial into 2.
Ma'am, 4 factorial into 2.
4 factorial into 2
Factorial.
Do you get the point here? Okay. How did you get, is it 4 factorial or is it 4 factorial into 2 factorial?
Ma'am, 4
4 factorial into 2 factorial.
Yes, ma'am.
Real-
4 factorial, 2 factorial.
Now, for what would it be for the case of in a circle? Think
3
about.
factorial into 2 factorial.
2 factorial into 2 factorial.
Is it 4 factorial, 3 factorial, n minus 1, or what would it be? So now, what would be my n here? These 2 people are always together, right? Right. So I have an A, B, C, D, E. Okay. And A, C, B, D, E. These 2 are always together, right?
Yes, ma'am.
Is
Yes.
that clear?
Yes.
Now, I want to tell you here, the clockwise and anti-clockwise is taken into account, but within this A, C, B and B, C, they can be either C is before B or B is before C. Is that clear?
Yes, ma'am.
Yeah. Okay.
Ma'am, can you repeat?
Okay. See, let's do this carefully. Okay. Let me take a smaller example. Let's look at this A, B, C, D alone. Okay. Right. I want B and C always together. How many ways can I do that? B and C are always next to each other.
3 factorial ways.
3 factorial.
3 factorial into 2 factorial.
In a line, I'm taking A, B, C, D. Okay. B and C are always together. First of all, how many ways can I arrange this? This is 4 factorial ways.
Yes, ma'am.
Yes,
Right?
ma'am.
Now, if B and C are together, how many ways can I do that?
3 factorial.
3
2
factorial.
factorial.
2
Factorial.
factorial into 2 factorial.
Into 2.
3 factorial. Till here, is everybody clear in a linear permutation way?
Yes, ma'am.
Yeah, ma'am.
Yes, ma'am.
Yes, ma'am.
Now
Yes.
let's come to the circular permutation. In circular permutation, how many ways can I arrange A, B, C, D if clockwise and anti-clockwise are different?
4 factorial ways.
3
It is 3
factorial.
factorial, n minus 1 factorial,
Yes, ma'am.
right?
3 factorial.
It is
Yes,
3
ma'am.
factorial, which is 6 ways. Till here, is it clear?
Yes, ma'am.
Yes, ma'am.
Yes,
Now
ma'am.
I'm saying B and C should be together. So how many ways can I do that?
2 factorial into
2 factorial into 2 factorial.
2 factorial into? Is it 2 factorial into 2 factorial?
Yes, ma'am.
3 factorial into
Yes,
2
ma'am.
factorial.
Factorial or 2
3 factorial
factorial?
to 2
B and C
factorial.
are together.
3 factorial into 2 factorial.
Ma'am, 3 factorial into 2
Why
factorial.
let it be 3 factorial? Yeah, it is.
Ma'am.
It is this B and C are together. So now it is 1, 2, 3 entities only, right? Got it?
Yes, ma'am.
If
Yes,
there are
ma'am.
3
Yes, ma'am.
entities, then it is 2 factorial. And among them, I can make two ways. So it is 2
Yes, ma'am.
factorial into 2 factorial. So you can see here, B and C are together here, 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 and here. Is that clear?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
So how many? It is 2 factorial into 2 factorial. Got it? Is it
Yes,
clear?
ma'am.
Yes, ma'am.
Yes, ma'am.
Now suppose clockwise and anti-clockwise are different.
2 factorial.
2 factorial.
2 factorial, ma'am.
That is
factorial.
only 2 ways, right? Agreed?
Yeah.
This
Yes, ma'am.
and this. Got it?
Yes, ma'am.
Yes, ma'am.
Got
So
it, ma'am.
this is how you are typically. So now I can extend this to many ways, right? Now the complement of this B and C do not want to sit together. These are the type of problems you look at, right? How many ways
Yes,
can I
ma'am.
do it?
Mhm.
B and C refuse to sit together.
So we can just subtract the number of cases.
Yeah, I
Eliminating
know
the
this is the
together.
total number of cases. The number of cases they sit to, total number of cases would be 4 factorial, right? In linear, right?
Yes,
Then it
ma'am.
is, it is
Minus
3
number of cases.
factorial, 2 factorial. So I subtract the number of
Yes.
cases they are together from the total number of cases. I'm going to get the total number of cases where they will never be together. Is this clear?
Yes, ma'am.
Yes,
So
ma'am.
these are the kind of problems you would have always. These are typical problems which are you. So similarly, when I come and I say that I have some beads, I want different colors to be next to each other. How many ways to do it? These are the type of problems you would have seen, right? Is it clear? I want certain types to be together, certain types not to be together. All of this is just an extension of the basic rules of this permutation and combination. Till here, is it clear, please?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes,
Right.
ma'am.
So when you are given problems of permutation and, so this was about permutation and circular permutation. Now, whenever we look at arrangement or order is important, I look at what is called a permutation. But if I'm not bothered about the order, so let me go back to this R objects from N objects. Okay, I said that the first one can be collected in N way and this second in N minus 1, and I defined this NPR, which was basically the number of arrangements of R objects from a collection of N distinct objects. Okay. Now, but if I'm not interested in the order or arrangement, then these R objects among themselves, how many ways can I arrange them? Is the question clear? If I have R objects among themselves, in how many ways can I arrange them? If I have just R objects, how many ways can I arrange them among themselves?
R factorial.
R factorial ways. Is that right? Okay. So each arrangement, okay, is going to give me R factor. See, I have, see, for example, I'm taking 3 objects from 5 objects. How many ways can I arrange 3 objects from 5 objects? Let's go back to this ABCD problem itself. Or let me go back here. Yeah. Okay, let me look at a simple ABC problem itself. Okay. Right. I have A, B, C. My n equal to 3. I want to arrange 2 objects from here. Okay, how many ways can I do that? I can, first one can be an A, second can be a B. First is an A, second can be a C, B, A, B, C, C, A, and C, B. Okay, so what is 3P2? It is 3 factorial by
2 factorial.
3 minus, no,
3
minus 2,
factorial.
1 factorial, which is
3 factorial.
which is 6. So this is 1, 2, 3, 4, 5, 6. Till here, is it clear?
Yes, ma'am.
Yes, sir.
Right? Okay. So now this is my N is 3. My P is 2. Okay. So my R is 2. My NPR, which is 3P2, which is 6 ways I have got this. Till here, is it clear?
Yes, ma'am.
Yeah.
Yes,
Right.
ma'am.
Now, I'm not interested in the ordering. That is, I don't care what is my first and what is in my second. In that case, this AB is same as BA.
Yes, ma'am.
Similarly, AC is same as CA.
Yes, ma'am.
And BC is same as CB.
Yes, ma'am.
Okay. In other words, each of my permutation is equivalent to 2 of my, each of this is equivalent to 2 arrangements. Is that right?
Yes, ma'am.
Yes, ma'am.
Right? Each thing is equivalent to 2 arrangements. So if I'm just looking at the combination of these 2, so if I look at combination, what will it be? AB and BA give rise to just AB. AC and CA is AC. BC and CB is BC. All these are the same. Is that right?
Yes, ma'am.
Yeah. So the number, if the arrangement is not this of concern to me, and I'm just looking at what is called a combination, then I have the number of possible combinations of R objects from n distinct object is nothing but n factorial by R factorial into n minus R factorial, which is the same as your NPR. This is my NPR divided by R factorial. So this is basically what is this? So in my example, I had 3P2, which was 6, which is same as 3C2 into your 2 factorial. So each one of the combination gives rise to one permutation. So you can see that I get that NPR is nothing but NCR into R factorial. Till here, is it clear?
Yes, ma'am.
Yes, ma'am.
Okay.
Yes, ma'am.
So this is about the combination. Now, very useful results are NCR is the same as NCN minus R. What this means is, the NCR is you're choosing R objects from N objects. If I'm choosing R from N, how many do I have remaining?
N minus R.
n minus r. So the number of ways of choosing r from n is the same as not choosing n minus r from n.
Yes, ma'am.
So this n choose r is the same as n choose n minus r. Is that clear?
Like,
And that can be mathematically shown
like
also.
for example, 5C2 will be equal to 5C3.
Exactly. Okay. But the understanding is choosing r is same as not choosing n minus r, right? So the number of ways I can choose r from n is the same as not choosing n minus r from n. Not choosing n minus r from n is same as n choose n minus r. Is that clear? Or
Yes, ma'am.
rejecting
Yes,
n
ma'am.
minus r.
Yes,
Okay.
ma'am.
And one very important thing is n choose n equal to 1 and n choose 0 equal to 1. And this identity, that is n choose r is n minus 1 choose r minus 1 plus n minus 1 choose r, is an important combinatorial identity. And this proof, I don't have the time to do this proof here, but I think I have already discussed about this in the lectures. This is an important combinatorial identity. Okay, this can be applied for certain problems. That is, if I want to know how many ways to choose r things from n things, it is same as choosing r minus 1 from n minus 1, fixing and r from n minus 1. This together would give me n choose r. Now, the main thing when it comes to your problem solving is, I need two things. First thing, given any problem, I need to understand whether I have to apply a permutation or whether I'll have to apply a combination. Remember, when the order matters, it is always a permutation. When the order does not matter, it is a combination. So let's do a certain reality check. Okay. The first thing is, if I want to have a password of 7 characters where the order matters using only digits. Oh, sorry, 4 characters, not 7 characters. If it is 4 characters or 7 characters also, but 4 characters for now. How many different passwords are possible? The password can start with a 0 also. And repetition is allowed. So first of all, is it a permutation or is it a combination? In a password, does order matter? Password or order matters. It's a permutation. How many ways can I have the first letter character?
10 to the power 4 total.
10. Second, repetition is allowed. 10. Third, 10. 10. Repetition not allowed.
10 to the power 4,
9, 8, 7.
9,
10
8, 7,
factorial.
which is 10
10p4.
4. Okay. So you can see that whenever I talk about a password, or so you'll find examples here, a combination of, in many things, you'll have a combination of uppercase, lowercase, numbers, and special characters. So you can see how even a simple 4-character password, how many ways you can do it. Uppercase, how many ways, how many uppercase numbers would I have?
26.
Uppercase 26. 26. Repetition allowed. Lower?
Yes.
26.
26. Numbers?
10.
Special characters? I can just say, if it is and exclamation. How many special character? 2. So now using this, you can know that if in a 4-digit password, it's going to be so many by, I can just say exactly one uppercase, or it should start with an uppercase. You can see how I can modify the problems. Is this clear?
Excuse me, ma'am. I have a doubt in this.
Yeah.
If repetition is allowed or not allowed is not mentioned in the question. Is it okay?
Yeah.
What should we assume? Should we assume that digits can be repeated? In certain questions like choosing a person or how, in what order people visit, we can infer from the context that repetitions is not
good
allowed.
question. See, it depends. For example, if I'm asking you to choose a team, okay, obviously when I ask you to choose a team with 3 people, I cannot have repetition there. I cannot choose a person twice. Would you agree?
Yes, ma'am. Yes, ma'am. That is
Whereas
true.
in a password, when I tell about a number, I can allow repetition of numbers.
Okay,
so I think that if it is not explicitly mentioned, The context of the problem should give you an idea as to whether repetition is allowed or not allowed.
Okay, in case of purchasing an item from a shop or any other normal situation involving objects, we can assume that repetition is allowed if it is not mentioned in the question.
Exactly. That's what I'm trying to say.
Okay,
Okay,
thank
so
you.
it depends on the context of the problem. Okay, yeah. Right. For example, every time when there are people involved, okay, when there are, you cannot treat people are distinct. That is something which you need to understand always. Whereas when I talk about balls, red balls, blue balls, okay, the context would be very different. Is that clear? Yeah.
Thank you.
Yes, ma'am.
Right. So the next problem, okay, is a pizza parlor. Build your own pizza. I'm giving you a choice. So if you go, I'm sure most of you must be using Swiggy.
Yes, ma'am.
No.
Yes,
So in
ma'am.
Swiggy, some of the restaurants give you an option to build your own meal. Have you seen that?
Yes, ma'am.
Yes,
They'll
ma'am.
tell you choose choice of starters, choice of mains, choice of all these things are given to you, right?
Customization.
Customization
Yes, ma'am.
available.
Right?
Yeah.
Customization. So in this case, how many meals can you make? Suppose I give you 3 choice of appetizers. Okay. 3 choice of appetizers, 4 choice of mains, and 2 choice of desserts. How many meals can you make?
I'm 3 into 4 into 2.
Okay, you can see that immediately the number of, okay, this is a very simple, but what you use every day in your life, you see that you're customizing. So if somebody asks you how many possible customizations can you have, you can list it. Now, similarly, in a pizza parlor, I am giving you a choice of 5 different toppings from a list of 10 toppings. Okay. How many unique combination of toppings can be chosen? First of all, is it a permutation or is it a combination?
Combination.
Combination.
Because I don't care whether I'm
Permutation.
choosing capsicum and cheese or cheese and capsicum, right? Both of them are
Order
toppings.
doesn't matter.
Order doesn't matter. But what does matter here? As repetition allowed or not allowed from the context? There is some
Allowed.
word
Ma'am.
which is giving it out.
Repetition does not allowed, ma'am.
That's not
Why?
allowed.
Repetition is not allowed.
Why?
Unique.
So
Unique.
here, is that clear?
Yes,
The
ma'am.
context, it's unique.
Yes,
So the
ma'am.
minute I say it is unique, I am not allowing anything of that. Is that clear?
Yes, ma'am.
Yeah,
Yes,
yes.
Yes, ma'am.
Yes, ma'am.
Right. So from the context of the problem, you can choose whether it is a combination or a permutation. And this is going to be just 10C5. Okay. 4-digit pin code. This is what we did
Permutation.
earlier.
Permutation.
A
Permutation.
bookshelf has 8 different books. I want to arrange 5 books. Permutation, combination.
Permutation.
Permutation.
I want to choose 5 books.
Combination.
Combination.
Okay, very good. So the first thing. Now again, this is a very, very popular permutation and combination problem, which is forming or choosing a team. If the team member roles and positions are distinct, okay, that is, if I ask you from 10 people, I want to choose a president, a vice president, and a secretary. Okay, are the roles distinct in this case?
Yes.
Yes,
Yes, ma'am.
So will it be a permutation or will it be a combination?
Permutation.
It would be a permutation. But if I just want to choose 3 committee members from a set of 10, are the roles
Combination.
distinct here?
Combination.
Combination. Right. So suppose I'm having athletic heats. Okay. And in the first heat, I just want to choose the top 3 winners. Will it be a permutation to the next round? I want the qualifiers, top 3 people go to the next round. Does order matter here or does order does not matter here?
Order
Does not matter though.
Combination.
Listen to me. I want to choose the 3 people from what kind of order would matter. I'm just looking at the top 3.
Yes, ma'am. Order is not important.
Odd.
Combination.
So how would you solve this problem? I'm having 5 people running a race. I want to choose the top 2.
Order matters.
Order matters.
Order matters. So permutation.
Top 2. Just think about it. Top
Permutation.
It's
The
combination.
combination means, ma'am, rank will
It's
matter. So
combination
rank
because
will
order
matter,
doesn't
It's
then
matter.
order will matter.
A, B, C, D, E are running a race. I want to choose the top 2. If A, B and B, A, will this be different or will this be the same?
Different.
It's same.
Different.
Same, ma'am.
It
will be same.
Different, ma'am.
Both are top 2.
Both are top 2.
Yes, ma'am.
But if I want to award one person the gold and one
But
person
the
the
position is
silver.
Order
different.
will matter.
Yes, ma'am. Then we
Com-
permutation.
See, the top 2 to get hold of whether but A, B or B, A among themselves do not matter. Is that clear?
Yes, ma'am.
Is the notion clear?
Clear.
See,
Yes,
top
ma'am.
2 is giving me an order, but I am telling I want to send the top 2 to the next level. Okay, so whether A and B come first 2 or B and A comes first 2, these 2 among themselves do not matter. Is that clear? You'll count them as the same.
Yes, ma'am.
Is that clear?
Yes,
ma'am.
Yes, ma'am.
Right. Okay, so that is important. Again, 4-letter code, we have already done this. So when we are looking at permutation and combination, first thing is we need to distinguish whether it is a permutation and combination. For that, I find out whether order matters, whether order does not matter. Again, whether it's a permutation, I look at distinct objects. Again, I see whether it is with repetition, without repetition, whether a circular permutation is asked for. Again, circular permutation, whether it is clockwise or anti-clockwise. Okay. And similarly, combination, I am going to apply the combinatorial identities that I have learned. Any question till here? Any clarifications or questions?
Yes,
Ma'am, I have a question. What do you mean by simultaneous communication?
Simultaneous?
Events.
Simultaneous events. Where did I talk about that? I didn't introduce probability yet.
No, ma'am, because
Ma'am,
I'm asking about permutation and combination.
Ma'am, Prashant is here. I think he's talking about EMQ. So we can discuss in EMQ related things in our session. We have mentioned in the beginning of the sessions. So ma'am will basically focus on the concept revision. So please ask doubt.
Okay, I think what Prashant he's meaning is whether the events are happening in the at the same time or not at the same time, right?
Yes, ma'am.
Yeah. Okay, I think as Prashant said, since I do not know the context, I don't want to confuse you. That would be discussed during the revision session. Okay, basically simultaneous, to just answer your question, is when things happen at the same time. It is what we refer to as simultaneously happening. Non-simultaneous is when it is something that is sequential. For example, I could pick up a ball, note the color and replace it and pick up the second ball. Picking up both the balls together is not happening in a simultaneous way. Whereas I throw 2 coins together, it is in a simultaneous way. Okay, so that's when I refer to a simultaneous occurrence or a non-simultaneous occurrence. Is that clear?
Yes, ma'am.
Okay.
Clear.
So now, any other conceptual doubts or clarification regarding permutation?
I had one question on circular
Yeah.
combinations. Sorry, circular permutations.
Yes.
So, so in the anti-clockwise and the clockwise permutation which is given, in that if it is asked that does the order matter? So are we saying that the order matters or?
I'm not sure I've understood. What do you mean by order matters?
Yes, ma'am. If they ask that while choosing a team, let's just say while choosing a team, we have fixed one position.
No, so in a table, okay, the closest I can think to is, suppose I am fixing that the order matters would be in the sense that the president sits next to the vice president, sits next to the president, and the treasurer sits next to the vice president. In this way, are you telling in that way?
Yes, ma'am. Yes, ma'am. One person is fixed and the others around. So in that way.
Yeah. So see the basic, the easiest way for you to always solve a circular permutation thing is look at it as a linear thing with order mattering, and then put it into a circle. Is that clear?
Okay.
See, this A, B, C, D also, I am looking at it in a linear way. I'm fixing this and I am making a circle out of this. That's why this B, C, D was n minus 1. This one. I was always attaching it, fixing it. Is that clear?
Okay.
So the same. Yeah.
So one more question was that
See, there is no circular combination part of thing, right?
yeah.
I'm only talking about it's an arrangement.
Okay.
Yeah.
So how do I identify like where clockwise matters and anti-clockwise matters and it does not
See,
matter?
typically when you are looking at, see, it's basically, I think unless it is specified, it is the clockwise or anti-clockwise do not matter. They are the same. But in certain situations, okay, in certain way, you want a particular arrangement. That is, I want B to be onto the right of A and not on the left. In that case, this is different from this. That's how you have to, it depends on the context of the problem and how you're going to look at whether the order matters or that is whether clockwise and anti-clockwise are same or different. Is that clear?
Yes.
Right? Okay. So I think there have been enough examples where the clockwise matters or anti-clockwise doesn't matter. We have not introduced, see, wherever there's an order that matters, look at the linear and apply the same circular permutation with a clockwise or anti-clockwise. Is that clear?
Yes, ma'am.
Right.
Excuse me, ma'am.
Yes.
I'm having a doubt in that concept. I'm confused that circle concept, circle permutation.
Yes.
You have said some example that beads in a garland. Can you explain that example, ma'am?
See, beads in a garland, right? Suppose I have 4 beads. Okay, a red, blue, green, and yellow. How many ways can I arrange them? In a line?
3 factorial.
4 factorial.
4 factorial.
4 factorial ways?
4 factorial. Yes, ma'am.
Now I want to make it into a garland. How many ways can I do it in a garland?
3 factorial.
Why is that so?
I'm fixing any one of them.
Yeah, the idea is whether it is a red, blue, green, or white, or a blue, green, yellow, or red, these two arrangements are same, right?
Yes, ma'am.
Is that right? These two arrangements are the same garland, right? When I'm looking at, whereas this red, blue, green, or yellow is not the same as blue, green, yellow, and red in a linear arrangement. Is that conceptually clear?
Ma'am.
That's why I am talking about fixing one and changing the others. The idea is the linear combinations are money more than the circular combination, because in circular I am having many of the linear would give me many of the circulars would be the equivalent of a linear. Is that clear? That's why I talked about the notion of fixing one. You're not physically fixing one. To get the formula, you are using this idea. Is that clear?
Yes, ma'am.
Yeah. So that's why it is n minus 1 factorial. Just look at 3. A, B, C. Okay. A, C, B. Right? What are the B, A, C, B, C, A, and C, A, B, C, 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 B, A. These are my linear combinations, right? 3 things. If I'm asking them to sit in a circle, how many ways can I do it?
2 factorial.
4 ways.
4 ways? How?
3 factorial.
6 ways, ma'am.
2
6 ways
factorial.
in a circle, in a circle. This is the way I'm
2
asking them to sit in a
6
line,
ways.
in a
2
circle.
factorial.
2
6
ways,
2
ma'am.
factorial, ma'am.
What are the 2 ways? A,
A, B, C, A, C, B.
that's it. This is when clockwise and anti-clockwise are the same. Otherwise, this ABC and A, but ACB are different, right? Right? But what about ABC this way? Are they the same or are they the different? If I'm asking them to sit in a, see, what is this? Was three
Linearly,
factors.
they will be same, ma'am.
Linearly, they are same, but in the circle, ABC
Yeah,
and
they are different.
ACB, are they the same?
No.
Why not?
No, direction-wise, they are different.
ABC and ACB, they are same or different? Clockwise and anti-clockwise?
They are different.
They are different.
ABC. What is
Same.
different? They're same, right? So what is N here? N is 3. N minus 1 was 2. If clockwise and anti-clockwise are different, it was 2 factorial, 2 ways. If clockwise and anti-clockwise are the same, it is just one way, which is ABC. I can make them sit in a circle in only one way. Is that clear?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
Yes,
Yeah.
ma'am.
So that is the idea that we have created here in a permutation and in a combination. Okay.
So,
See,
so in this question, if they specifically mention that please take ABC and ACB as different, then it's 2, or else it's 1 only.
yes, yes.
Okay.
Otherwise, see, that's what I'm saying. When I'm asking you to make 3 people sit in a round table, how many ways can I make them sit in a round table? A, B, C. This is only one way because this is the same as A, B, C. Again, here the clockwise and the anti-clockwise. So it depends on which is the position of the, but however, if I say the head sits here and the other sits here, then the head position is here and this BC or BC, it is going to be one or the 2, right? Okay, that's why it is only 2 ways to do it. Is it clear? Yeah?
Yes.
So that is the idea of, see, by fixing the position, that idea was to come up with a formula. But basically what it says is every circular combination or permutation gives rise to multiple linear, this one. It is not the same. See, AB, DC, CD is the same as BCDA, which is the same as CDAB when it's circular. Agreed? Which is the same as DABC, right? But linear, they are very different. Do you see that?
Yes, ma'am.
Okay, that's what is the idea. Okay. So now moving on to any more clarifications from the permutation and combination part?
Ma'am?
Yeah. Yeah, I think we'll take the first person first. Yeah, go ahead.
Ma'am, how to identify in a given scenario whether clockwise and anti-clockwise are same or different?
See, most of the times, okay, right?
Yeah.
Most of the times it would be that the things clockwise and anti-clockwise would be same unless specified. But again, it depends on the context of the problem where the clockwise and the anti-clockwise could be very different. Okay. Most of the time, the clockwise and, for example, if I'm setting up numbers on a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that clockwise is different from the anti-clockwise, right?
Yeah.
If I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 or something, okay, this is the clockwise direction, this is the anti-clockwise. So that depends on the context again. Okay, and based on the context, you can always decide. Is that clear?
Okay, ma'am, if a bracelet is the same in the mirror image, can we say that clockwise and anti-clockwise are same?
Yeah, exactly. That's what I'm saying. Bracelet, garlands, they are the same, right? Okay.
If the mirror image is the same,
yeah,
then we
mirror
can say
image is the same. You can say, yeah, it is right. There was another question.
But that's it, ma'am. Thanks.
No, there was another question from some
Yes,
other
ma'am.
person. Yeah.
Can I ask?
Yeah, please.
Ma'am, why we multiply 3
Can you be
factorial?
louder, please?
Yes, ma'am. Ma'am, why we multiply 3 factorial into 2 factorial when BC are together in factorial permutation?
One second. Are you referring to this question when I said two people are together?
Yes, yes, ma'am.
Yeah. So see, when I'm having, let's look at just a simple thing, A, B, C. I have three people where B and C always say they are going to sit together. How many ways can I arrange them in a linear way?
6 ways.
6 ways? In a linear way. B and C are always together.
2 factorial.
2 ways, ma'am. 2 ways.
Just 2 ways. It's
Yes,
either
ma'am.
A, B, C.
Yeah. Or CBA.
It could be BCA also, right? Just look at it. How many ways can I do it? It could be BCA. It could be ACB. It could be CBA, right? Agreed?
Yes, ma'am.
Agreed.
Yes, ma'am.
Right?
Yes.
So if you look at it, these two, okay, I'm treating BC as one. These two are the same permutation. If I'm treating BC as one entity, BC and CB are the same. BC and CB are the same. This is the other one. These two are the same. Agreed?
Yes, ma'am.
But
Agreed,
between
ma'am.
BC, I could have a BC or a CB, BC or a CB, right? So it is 2 factorial and this into 2 factorial. So it gives me 4 ways. Is that clear? Or do you
Yes,
want me
ma'am.
to explain again?
No, ma'am. Yes, clear.
Is it clear?
Clear.
So suppose
Yes,
I have A, B, D, C. Now, tell me how many ways a BC have to be together. How many ways can I do that? Now, this BC is a block. How many ways? So it would be 3 factorial. And among them, I can do it in 2 ways. So it is going to be 2 factorial ways. Is that clear?
Yes, ma'am.
Yes, ma'am.
Right?
Yes.
So now suppose I have 3 people who are always going to sit together. What would be the number of ways I can do it? A, B, C, D, but B, C, D always want to be together.
2 factorial.
2 factorial into? These B, C, D
3
always want to be together.
3
Into 3 factorial. Is that clear?
Yes, ma'am.
Yes, ma'am.
Yeah?
Yes.
Okay. Any other questions?
Yes, ma'am.
Okay. So
One
now,
question.
yeah, right,
Yeah,
please?
so
Yeah.
for the simultaneous and non-simultaneous ones. So an example, let's just say we are choosing a password with 0 to 9. Is the selection of digits happening? Is this happening simultaneously or not simultaneously?
Okay, selection of password. So let me take your same question. So I'm not sure as to what is the simultaneous and non-simultaneous from the assignment point. Okay, but I just want you to say that what are you doing? You are basically choosing a password with, suppose I'm choosing a 4-letter password, right?
Right.
Okay. So what does that mean? I can choose a first, second, third, fourth. Right? If I'm choosing this, if repetition is allowed, I can do this in 10 ways, this in 10 ways, this in 10 ways, and this in 10 ways, right?
Okay.
Agreed? Now, if repetition is not allowed, I can do this in 10 ways. Once I have chosen this, I have only 9 available for this. Once I have done this, I have 8 available for this, and I have 7 available for this. Is that clear?
Yes.
So in this way, I can in some sense think that I am simultaneously choosing all these 4 blocks and I have 10 ways of doing it. Whereas in this second case, once I've chosen the first one, I have to then do this. The second one is not chosen simultaneously. It is chosen after I have chosen something here. Is that clear?
Okay, so it is more the question of repetition or not repetition, right?
In some sense, yeah. But in this context, it is more like repetition or non-repetition. It depends on what is simultaneous is. And again, it could come as in a thing that there could be problems where I am choosing balls from 2 buckets. I choose a ball from the first bucket, note its color, and then choose a ball from second bucket. So this is a non-simultaneous way of doing it. Do you see that?
One ball.
Yeah. I
Okay.
choose a ball, note its color, replace it, and then choose a ball from the second bucket. You'll have problems of this kind also, right?
Yes.
So this is not simultaneous. Suppose I'm tossing the two coins at the same time. That is again simultaneously doing it. Is that clear?
Yes.
Okay. Right. So I think with this, let me move on to the probability portion, because we just have about an hour to review concepts here. If there are no more questions, I'll move ahead.
Ma'am,
Yeah.
ma'am, can I ask a question from descriptive statistics?
Now,
It's
no, sorry,
one
no,
of
no,
the
no, no. I think not
debated.
now. Not now. Okay, because this is very specific, and I think we have only about 50 minutes left. So I just want to complete whatever has been planned. Okay. You can anytime you have a question, please put it on the discourse. If that question needs my attention, I will always take care of it. Okay.
Okay.
Right. Thank you. So the next thing is, the main reason why we learned about permutation or combination and counting is because whenever we want to know the probability, and probability is also very important because we are living in a world of uncertainty. We are not having anything that is certain. Okay. I cannot tell for sure that this is going to happen. I cannot tell for sure that tomorrow I am going to have 25 people who are attending my class. I can only say that I could have around 25 who are attending my class. I cannot say for sure that definitely this is going to happen. There is a element of uncertainty. Whenever there's an element of uncertainty, I need to capture this element of uncertainty, and the theory of probability helps me capture this element of uncertainty. For example, we are always want to know, today is a WPL final, right? You all watch Women's Premier League?
Yes, ma'am.
No, ma'am.
So, no?
Yes,
Okay.
ma'am.
For those of you who watch, nobody follows women cricket. That is sad. Today is a women WPL
Yes,
final.
ma'am. RCB versus Delhi.
Yes,
Yeah,
Bangalore
who do
and
you think
DC.
would win?
RCB versus MI.
Do we know who is going to win?
Am I not Delhi?
RCB.
RCB.
No, my
Definitely
question is,
RCB,
do we
RCB,
know
ma'am.
who is going to win?
No,
No,
ma'am, we
ma'am.
don't
No,
know
ma'am.
who's
We
gonna
don't
We
know.
don't know, right? There's
We
an
can
element
guess,
of
ma'am.
chance
We
there.
have a
Okay.
probability.
We
So
can
what
only
is the
predict.
random? What is it a random experiment? If I tell it's a random experiment, what are the outcomes of this random experiment today?
either RCB or DC will win, ma'am.
50-50 chance on both.
50-50 chance. Again, you are assuming everything is equally likely to happen. Okay.
No, ma'am.
Do you people again follow commentary on any of the websites? Do they always tell that there's a 50-50 chance?
No, ma'am.
Which is more
Depends on
likely to win the
Smith
cup?
Petra.
Is it Delhi Capitals or RCB?
Google actually
Delhi
says
Capitals.
that 58% chance of Delhi Capitals and 42% chance of RCB winning it.
Right. Okay, that's what Google says, right? So now you can see that this is a real application of what we learned in probability. What are the sample space here? Either RCB wins or Delhi Capital wins. Is a tie allowed in the final?
No.
No.
No,
What
ma'am.
No,
happens
ma'am.
if they tie?
Super over.
Super over.
Super over.
Super over.
Super over. What happens even after the super over?
Again,
One more
there is a
super
super
Again,
over.
1 over.
Yes,
Again,
ma'am.
there's
There
a
is
super
super.
over. What would happen even after that?
Wicket
Boundary
What
counting.
a result,
Only
right?
Boundary.
These are
That is
always
based on
decision.
boundaries.
right. There are always result driven. So what is a random experiment? So here I know the outcomes. What are the outcomes of this experiment? I know either RCB would win or Delhi Capital would win, but I do not know with certainty which outcome is going to happen. Is that clear? So there is what I want you all to understand is, many people say that a random experiment is an experiment where the outcomes are unknown. It is incorrect. The outcomes are known. I know it would be either RCB winning or Delhi Capitals winning, but there's an uncertainty about which is going to happen. Is that clear? Is the notion clear? Outcomes are known, but which of the outcome would happen, there is no certainty about that outcome happening.
True.
Okay. So this is the sample space. A sample space lists collection of all possible outcomes. And typically, can RCB and DC win together?
No, ma'am.
No, ma'am. No, ma'am.
No. Only
No,
RCB
ma'am.
wins or
Tie is not
DC.
allowed.
Okay,
Yes,
right.
ma'am.
Okay. Now the next thing is, okay, assume that how many teams were there? Okay, if you all don't like
6
WPL, IPL, how many? 6 teams.
Five.
Yes,
There
ma'am.
were 5 teams.
Teams.
6 or 5
Five.
teams.
Five,
Yeah.
five
Five.
teams.
5 teams.
Okay. Right. So at the beginning of the tournament, what would have been the sample space?
5.
RCB,
5 teams.
DC, Mumbai Warriors, UP, Mumbai Indians,
Gujarat
UP
Giants.
Warriors, and Gujarat Titans, Gujarat Giants or something, right?
Thanks.
Okay, right. Now, any one of them could have won. Now, again, as you say that today's match, it could be either RCB or DC. And we also see that there is no equal chance. Somebody said that DC was given 0.58 and this was given 0.42, right? That is what you are saying.
Yeah.
Is that right? One of you told me that.
Yes.
So the outcomes need not be equally likely also. They could be different probabilities assigned to them. And how do we get this probability? From where do I get this probability? DC is 0.58 and RCB is 0.42.
Analysis of
It could be
Conceptual
past data, right?
performance.
Past data gives me an
Yeah.
estimate of these probabilities. That is what it is. No person is sitting under a tree to tell that, okay, DC will have 0.58. It could be how are we coming up? We are estimating these probabilities. Is that okay?
Yes, ma'am.
Right? Okay.
Yes,
So now, given any such problems, a subset of the sample space is what we call an event. Okay. So now, what could happen is that let me look at all possible games that have been played. I'll have an entire list of these games. Out of that games, that could be my sample space. Agreed? All possible games. Or all possible games, RCB is one, all possible games. So it depends on how we are defining the outcomes of the sample space. Each team played about 8 games or something. And for each of those games, I can give what have been the outcomes of the game. An event could be the games in which RCB has won. Or I could just look at the games which RCB and DC have won. I could look at all the games RCB as one and DC as one. And so that is how we can define events which are nothing but subsets of my sample space. Okay. So just one thing which we need to understand from this probability is I can look at my sample space as the whole universal set from set theory. Events are subsets. So the minute I look at event a subset of a sample space, the basic set operations which are union and which are intersection would happen. So let's look at a very simple quiz, this one of tossing 2 coins and noting the outcomes. What is the sample space here? I'll just take a minute and all of you can write it down in your paper. What is the sample space?
Head, all the teams.
Ma'am, 4.
And equivalent, this is you people are taking 2 exams, okay? And the outcomes are just pass and fail. So what would be the sample? Instead of tossing 2 coins, let me say 2 exams. Okay, and the outcome of each exam is only a pass and fail. What is the sample space in this case?
Pass in both the exams. PP,
Okay.
PF,
FP,
FP, and FF.
Yes, ma'am.
Okay. What is the thing of passing in the first exam?
2.
PP and PF.
1 by 2.
Passing in the second exam alone?
FP and
FP and PP.
And
Passing in the second exam. Passing either in the first or the second?
PP.
PP, PF, and FP.
Yes, ma'am.
Passing in the first and the second?
PP.
PP only.
Okay. So this is again similar thing is, okay, I am going to families with 2 children and noting the gender of the child. What would be the sample space? Gender and of the child of the 2 children. And the order also, the first child and the second child. What could be the sample space?
Male,
The first
male,
is
male,
male.
female.
The first one is a male,
Female.
Female,
female,
and
male.
male, and both female.
Both are female.
Right.
Yes.
So I can define similar things. So you can see that analogously we can define a lot of things. Agreed? So the sample space and each one is giving me an event. So here, what would be the equivalent event here? Head on the first or second is the male child is either the firstborn or the secondborn, right? Okay. And what would be this? Both born are male child. Is that clear?
Yes.
Yeah. So you can see that we can define events, both the union of events and the intersection of events. The null event is the event which does not have any outcome. And if 2 events have, that is, if 2 events cannot simultaneously occur, we say that they are mutually exclusive. That is the occurrence of the first event. That is the occurrence of a head. Can head and tail happen at the same time simultaneously? No.
No, ma'am.
So they are mutually exclusive events. And just as we are talking about all the basic set operations, we can talk about the complement of a set also. So what is the complement of head down at first toss?
Tails.
Tail on a first toss. That would be TH and TT. Okay. So we can talk about complements of a thing. So you can have head on a first toss as HHHT, tail on a first toss as THTT. You can see that complements are mutually exclusive. Okay. So now we can use this using Venn diagram. You have the representation E union F is the entire shaded region, whereas the shaded in dark is E intersection F. This notion is very important for us when we introduce the notion of conditional probability. But for us to actually write down the probability of an event, we set up first what is called the probability axioms. Okay, just as probability, you have the subjective way, the empirical way, and all of that. One of the most important ways of assigning probability events is what we call the axiomatic approach, which is coming from 3 axioms. The first axiom says that for any event, the probability of the event is a number between 0 and 1. The probability of the sample space is 1. This actually means that the outcome would definitely be an element of the sample space with probability 1. That's what it means, that the probability of the sample space is 1. And the third says that for a sequence of mutually exclusive events, the countable union, the left-hand side is nothing but a countable union. The probability of the union is the sum of the probabilities. These 3 axioms lead me to get what is the probability of the complement of an event. If the probability of the sample space is 1, I know that the probability of the sample space, okay, E union E complement is the sample space. I can get the probability of the samples. E union E complement is sum of probability because E and E complement are disjoint. Okay, the axiom 3 says the probability of the union is the sum of the probability. To get that, the probability of a complement is 1 minus probability. And similarly, the probability of a null set is equal to 0. So the third rule, which was third axiom, which applies to probability of countable union, can be applied to probability of finite union. In general, if I have probability of even union E2, which is a finite union of 2 sets, even and E2 are disjoint, it's the probability of the sum of the probability of the events. Now, this generally what happens is we have what is called the addition rule of probability. Now let me look at E1 and E2. If they are disjoint, then I know probability of E1 union E2 is probability of E1 plus probability of E2. This is what my addition rule tells me. What happens if they are not disjoint? In other words, what would happen to the probability when I have two events which are not disjoint? So I have a E1, I have a E2, I have a E1 intersection E2. The idea here is I can write this entire shaded region of vertical lines, this hard shaded region which is E1 intersection E2, and horizontal line. Let me call this region 1, this region 2, and this region 3. Would you all agree with me if I wrote E1 union E2 as 1 union 2 union 3? Can I write
Yes.
E1? Yeah?
No,
Yes,
ma'am.
ma'am.
Why not?
No, ma'am.
Because 2 includes both 1 and 3.
No. 1 is only the vertical lines.
Yes, ma'am. Yes, ma'am.
3
Then it
is
will be.
only
Then
the
it will be.
horizontal line. 2 is this shaded region. So E1 union E2 is 1 union 2 union 3. Would you all agree now?
Yes,
Yes,
ma'am.
Yes,
Yes.
yes, ma'am.
If that is the same, that probability of E1 union E2 is the same as probability of 1 union 2 union 3.
Yes, ma'am.
Yes,
Are
yes,
1,
ma'am.
2, and 3 disjoint, mutually exclusive?
Yes.
Yes, ma'am.
No, ma'am.
Yes, ma'am.
No, ma'am.
Not.
Why?
No, ma'am.
Why?
Yes, ma'am.
1 is only the vertical. 2 is only this region. 3 is this region.
They are mutually exclusive.
They
So
are
can I
disjoint.
apply
So
the third axiom to write this as probability of 1 plus probability of 2 plus probability of 3?
yes.
Yes, ma'am.
Yes, we can.
Yes, ma'am.
Right. But what is probability of 1? What is only 1? 1 is E1 minus your 2, right? 1 is nothing but probability of E1 minus probability of E1 intersection E2.
Yes,
Yes,
ma'am.
ma'am. Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Probability of 2 is just probability of E1 intersection E2.
Yes, ma'am.
Yes, ma'am.
Probability of 3 is probability of E2 minus probability of E1 intersection E2.
Yes,
Yes,
ma'am.
ma'am.
Yes,
Yes,
ma'am.
So
ma'am.
I have probability of E1 union E2. These two can cancel out. This probability
Yes.
of is probability of E1, which I get from here, plus probability of E2, which I get from here, minus probability of E1 intersection E2. This is what we call is the addition rule of probability. Is this clear?
Yes, ma'am.
Yes.
Yes,
Yes,
ma'am. Clear.
This addition rule,
clear.
how do I apply this addition rule? So here I have a customer who goes to a clothing store. He can purchase a shirt with probability 0.3 and a pant with probability 0.2 and both with probability both a shirt and a pant with probability 0.1. What is the problem? If S is the event of purchasing a shirt, what is probability of S? Probability of purchasing a shirt. It's given to you.
0.3.
0.3.
0.3.
Probability of P?
0.2.
0.2.
Okay. Now I want the proportion of customers who purchase neither a shirt nor a pant.
0.6.
1 minus union and
Yeah. So what is probability of S union P? Describe this event.
P of
Ma'am,
S
PS
P
plus
of
PP minus
minus
PS
P
No,
of
I
S.
want
intersection
you
P.
to describe this event. S union P is the event
Either
of a
shirt or
customer,
pant.
Either shirt or pant.
shirt or pant.
And yes.
What is this probability? This by my addition rule is probability of S plus
0.4 will be
probability
the
of P
answer. And
minus
final
probability
answer
of
will be
S
0.6.
intersection P,
Yes,
which
ma'am.
is
0.4
0.3 plus 0.2 minus
minus
0.1, which is 0.4.
0.4.
Right? This is the proportion of who buy either a shirt or a pant. But I want neither a shirt nor a pant, which
1
is the
minus
probability
0.4.
of the
1 minus
complement,
0.4.
complement,
which
yes,
is
ma'am.
1 minus 0.4, which is 0.6.
0.6.
0.6.
Is that clear? So
Yes,
this
ma'am.
is applying your addition rule and the complement rule to purchase this. So from the context of the problem, identify the events, translate the that is proportion of neither is probability S union P complement. S union P complement is nothing but 1 minus probability of S union P. Find out S union P using the addition rule. Find out S union P complement using the complement rule. Is that clear? Yeah?
Yes,
ma'am.
ma'am.
Okay.
Yes, ma'am. Clear.
Right. So the next thing is we talk about equally likely events. So rolling a dice is an equally likely event where I have a fair die. Okay. What is the probability of A here? Where it is a outcome is an odd outcome.
3 by 6.
Yes,
3 by
ma'am.
6.
3 by
Very
6.
good.
0.5.
B the event that the outcome is greater than 4. What is the probability of B here?
2 by 6.
2 by 6. C is either odd or greater than 4. What are the outcomes of C? Either odd or greater than 4. What are the outcomes? What are the outcomes?
4 by 6.
2 by 6.
2, 3, 5, 6.
It's either odd or greater than 4.
1 by 6.
1
Ma'am,
by
you
6.
I'm
need a
asking what are
6.
the outcomes.
4 by
I'm asking what are the outcomes.
1 by 6.
1356.
1, 3.
56.
Do you all agree?
No, no, ma'am. It is only 5.
Either odd or greater than 6. I didn't say and. It is either odd.
Yes,
Either
ma'am.
odd is
1, 3, 5, 6.
5 or greater than 4.
5, 6.
5,
Yeah.
6.
1, 3,
5,
5,
Right.
6.
So
Yes,
what
ma'am.
are the outcomes? 1, 3, 5 and 6. So there is an intersection
4 by
which is
6.
5. Okay. So the probability is 4 by 6. Is that clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
1, 3,
Yes,
5,
ma'am.
6 is 4 by 6. Okay. Right. So the next thing and a very important concept is that of conditional probability. Now suppose I go back and roll or let's go back to rolling our dice. Okay.
I have a question.
Yeah.
Yes, ma'am. I have a question regarding cards. So let's just say if we had an event of drawing a king and an ace consecutively from the deck. So I mean, how would you approach it from a Venn diagram? Like if you were to draw a Venn diagram for this, like drawing a king and an ace consecutively, that is the event. So
So drawing what is the event here? Drawing a king, right?
drawing a king and an
Okay,
ace
let me call that
consecutively.
K.
Yeah. And then consecutively.
So what is the probability of drawing a king?
King is 4 by
4
by 52.
4 by 50.
Right.
4 by
Ace.
13.
4 by 52.
4 by 52.
So the outcomes are, so you're drawing 2 cards.
Yes.
Right.
Yes, ma'am. Yes.
Right. So when you're drawing 2 cards, the outcome is card 1, card 2. And what are the possible ways of drawing card 1 and card 2? Obviously, I'm drawing 2 cards. Is it with replacement, without replacement? You
With
tell me when
replacement.
I'm drawing 2 cards. With replacement, can I have the first card drawn the second time also? I'm holding 2 cards together, right?
Okay.
So again, the context, if you're just drawing the card, noting the card and replacing it back, then what is the game that you're talking about? Are you drawing 2 cards and holding 2 cards? Or are you just going to pick up a card, note it and replace it?
Yeah, pick up a card, note it and replace it.
Okay, that's fine. So the first card could be any of the 52 cards.
Right.
Right. The
Yes,
second
ma'am.
also could be any of the 52.
Right.
Right. Okay. Now you are saying that what is the chance that the first card was a king and the second was an ace? Or what is the chance of a king and an ace being a part of it? The order does not matter. What is the question that is being asked?
The question is, the first card should be a king and the second card should be an ace.
So the way you're going to frame it is, what is the chance the first card is a king? Right. That would be 4 by 52.
Okay.
And second card is an ace given the first card is a king.
Okay.
Is that clear?
Right.
So that is where I have my notion of conditional probability appearing. Is that clear? So let me so I have a tossing two coins. This is my sample space. TT, agreed?
Right.
Right? Okay.
Yes, ma'am.
Now, what is the, suppose I define E1 to be the event that my first toss was a head. What are the outcomes?
Head.
Head.
Head tail.
Tail. I am defining E2 to be the event that my second toss is a head.
HH and TH.
HH and TH.
HH and TH. Right? Now I'm defining another event which is telling me that the second toss was a head given condition that my first toss was a tail, a head.
Sorry,
What is the outcome which is telling me that the second toss is a head conditioned on the fact that my first toss also was a head?
HH, ma'am.
That is only HH. Would you all agree?
Yes. Yes.
Okay. So now if I look at the chance of that happening, it is just this, okay, the chance of the second toss being a head given that the first toss was a tail. So now let's look at why is this conditional probability and all of that very important. So let's, because it's too late in the night, let me give you a very simple, all of you would have seen game shows of this kind. This is a very famous game show called the Monty Hall problem. Okay. Now I have 3 doors. Suppose I'm the host of this game show. There is a car behind one door and there's a goat behind 2 doors. Okay. I'm asking you all to choose a door. Okay. Give me one choice. Any one of you play it with me. Give me a choice.
1, ma'am.
3, ma'am.
1. Okay. So you have chosen 1. I am going to open one of these 2 doors and that will reveal a goat. So I open door 3 and there's a goat. Okay. Now I'm giving you a chance to change your decision. Would you choose door 2 or would you stick to door 1?
I will stick 1.
Huh?
Door 1.
Is the question clear?
Yes, ma'am. Yes.
Stick to 1.
You'll stick to 1. How many of you will stick to 1? How many of you will change the decision?
Ma'am, probability is same for both, right? So
Why? No, why? That is the thing. See here, what was the chance that there would be a car behind door 1, door 2? This is a very interesting problem. What is the chance that you could have a car behind door 1?
33% each, ma'am.
1/3, 1/3, 1/3, right?
Yes, ma'am.
Yes, ma'am.
Okay. Now I'm telling you there is a goat behind door 3. Now what would be the chance? Okay. Right. Of finding a car behind, given that there was a goat behind door 3. Will it be the same as probability of C2 or will it be lesser?
Lesser, ma'am.
Lesser, ma'am. Yeah.
Lesser, ma'am.
Will it be lesser or will it be greater? Think
Uh,
about it.
greater.
Do this
Greater.
problem.
Sorry, ma'am. Greater.
Will be greater.
Will this be the same or will this be greater?
Greater. It will be greater.
Greater.
Then will you switch or will you retain it?
Will retain.
Will
We
switch
will
out.
retain.
If the probability of C2 conditioned on D3 is greater than the probability of C2, will you switch or will you retain?
Retain.
Why will you retain? The probability of me, initially I chose door 1. Okay, because, and now what was the probability of you getting door 2? It is also 1/3. So between door 1 and door 2, you are agnostic, you were choosing door 1. Now I'm telling you there's a goat behind door 3. Now I'm saying, do you think that the probability, will you switch or, so I'm asking you, will the probability of you finding a car behind door 2, given that there was a goat behind, conditioned on the event that there was a goat behind door 3, will that be higher than your initial probability of finding a goat behind door 1? Think about this problem.
Yes,
This is a very
it's higher.
interesting
It will be
problem.
higher.
It's higher.
And what you, so you
Because
can see
two
that
goats together is very less probable. So goat
See,
and
I'm
car
not going to
together is
open
very.
a door. See, suppose there was a car, I'll open only a door. See, if there is a door behind this, the car, now initially I had three uncertainty. Now I have resolved one uncertainty, right? I'm showing you there's a goat behind one door. I just want you to think for yourself as to what would happen to the goat. Okay, think about it. Okay. Now coming back to conditional probability, what the notion of conditional probability says is, I want to know what is the probability of an event happening conditioned on some other event happening. So let's go back to one of the most popular examples which we have already discussed is rolling two dice. Okay. The possible outcomes are 1, 1, 1, 2 up to 1, 6, 2, 1, 2, 2 up to 2, 6, 6, 1, 6, 2. I have 36 possible outcomes. Agreed? Yeah?
Yes.
Now let me define an event even to be the sum of outcomes is 7. What is the probability? What are the outcomes in this even? The sum of outcomes is 7. What are the possible outcomes?
1 6 6 1
6,
1
6,
6
6 1 4 3
3
3
4
4
4 3
6 by 26.
5, 5, 2,
3 4 4 3.
4, 3. Okay?
Yes, ma'am.
Yes.
Right. Sum of outcomes is 8.
4 4
4 4
4 4
6 2 2 6
5 3
5 3 3 5.
Yes, ma'am.
7 1 1 7.
Hey, 7 1. From where will I get 7 1?
7 was not there.
From where will I get 7 1?
Yes.
Maximum outcome.
Okay. Right. Okay. Let's look at E1 and E2. Now let me define a E3 to be the outcome of the first toss. What are the possible outcomes? First toss.
1 2 3 4 5 6.
1 2
3
3
4 5 6.
4 5 and 6. Okay. Right. Now E1 is sum of outcomes is 7. E2 is sum of outcomes is 8.
8.
Right? Okay. Can I get an outcome of 7 irrespective of what was my first toss?
Yes, ma'am.
Think about it. Can I get an outcome of 7 if the outcome was a 1?
No,
Yes.
Why not?
Yes, we can
The
get
outcome
1
was
comma
1,
5, 1
1
comma
and
6.
6.
6.
If outcome was 2, I can get a sum of 7. Outcome was 3, I can get a set of 7. Outcome was 4, yes, 5, yes, 6, 1. Can I get an outcome of 8 irrespective of what was my first toss?
Yes,
No,
ma'am.
ma'am.
No.
No,
No,
ma'am.
ma'am. At least 2 should be the outcome at the first toss.
Right.
Then
Okay.
only you
So
get 6 and
now,
you can get
so
8.
without any mathematics, is the getting an outcome of 7 dependent on what was your first outcome?
Yes, ma'am.
Getting an outcome of
Sometimes it is,
7,
sometimes
get
not.
the sum of getting a sum of outcome is 7. Is that dependent on what was your first outcome?
No,
It's
ma'am.
not dependent.
No, ma'am. No, ma'am. No, ma'am.
But getting a sum of 8, was it dependent
ma'am.
on what was
Yes,
your first
ma'am.
outcome?
Yes,
Yes.
ma'am.
So are E1 and E3 dependent?
Yeah, ma'am.
E1 and E3 are not dependent.
Dependent.
E2 and E3?
Dependent.
Are dependent.
Are dependent.
Yes, ma'am.
So through an example, we can, and just by basic understanding of dependency, we see that E1 and E3 are not dependent, whereas E2 and E3 were dependent. Is that clear? So now let's put some math into it. So I wanted to ask probability of E1 happening given E3 happened. Okay. So what is this? What is the chance of E1 happening given E3 happened? So that is what we are defining as. So this is your E conditioned on F. So I know that this portion, this red portion divided by the total portion is the probability of E happening conditioned on F. See, F happening only is this blue portion. Would you all agree? F is this entire blue portion.
Yes, ma'am.
Yes, ma'am.
Yes.
The portion of E happening conditioned of this F is this. So this is this red divided by this blue would be the probability of E happening conditioned on F. Do you all agree? The fraction of E happening, this red conditioned on this entire blue. Okay, which is nothing but the red is your probability of E intersection F. This blue is your probability of F. So the probability of a conditional probability is nothing but the probability of the intersection divided by the probability of the total event. Is this clear, please? The understanding of what is conditional probability?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Right.
Yeah.
So if you go back to your initial weeks, we did this association table. If you remember, the example we took was ownership of a cell phone and gender.
Yes, ma'am. Yes.
Right.
Yes, ma'am.
And here I wanted to know what is the person who is owning condition, then they were a female. So I looked at what was the ownership and female and divided by this. This is ownership intersection female. Yes, this is no intersection female. Concept of relative frequency was introduced. Very similar to that. Is that clear?
Yes, ma'am.
Yes.
Yes, ma'am.
This is what we refer to as a conditional probability. Now, in this conditional probability, let's look at what is probability of even intersection with E3. So what does this mean? This is the probability of, this is nothing but divided by the probability of E3. What is probability of E3? That is very simple, that whatever is my first toss. Okay, so suppose I'm asking you that the first toss, so I want to know whether probability, let me define this way. 1 second. Okay, let me define E1 to be 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. Okay. Let E2 be, the first toss was a 4. That E3 I defined was anything of my first toss. I'm telling the first toss was a 4. Okay. So what are the outcomes in first toss was a 4? It is 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, and 4, 6. Right? Let E3 be the event that the sum was a 8, which is 2, 6, 3, 5, 4, 4, 5, 3, and a 6, 2. I have not missed out anything, right?
Yes, ma'am.
Yes,
Okay.
ma'am.
Now,
Yes, ma'am.
let's look at, so I said that from this, so I want to first look at probability of even conditioned on E2, which by definition is probability of even intersection E2 divided by probability of E2. Is this clear?
Yes, ma'am.
What
Yes,
is
ma'am.
probability of
Yes,
even
ma'am.
intersection E2?
4, 3.
Only this
4
one,
to
4,
1.
3.
4, 3. Yes.
Right? Only one event, right?
Yes.
Yes,
Yes, yes, ma'am.
Even intersection E2 is only one event, which is
1 by
4,
30.
4, 3.
which is 1 by
4, 3.
36,
Yes.
right?
Yes.
What is the probability of E2? It is 6 by 36.
Yes, ma'am.
The probability of even conditioned on E2
1
is
by
1 by
6.
6. What is the probability of even?
Even
6 by 36?
6 by 36.
6 by 36.
So 1 by 6?
1 by 6.
1 by
Yes,
6.
Okay, right. Now let's look at what is probability of E3 conditioned on E2. Okay, what is that? E3 conditioned on E2?
E3 intersection E2.
E2, what is that?
1
4,
by
4.
36.
4, comma
That is
4,
just
ma'am.
4,
4, 4.
4, comma 4.
Is
Yes,
again
ma'am.
1 by 36.
1 by
Yes,
36.
1 by
E2 is
36.
again 6 by 36, which is 1 by.
1 by 6.
But what is probability of E3?
5 by
5 by 36.
5 by
5 by
36.
36.
5,
So
1,
you
2,
see
0,
that
5 by
this
36.
is not the same as E3, whereas this was the same as E1.
Yeah, ma'am.
Agreed?
Yeah.
Which
Yes, ma'am.
tells. Now this is the answer will not change whether this was even a 3. First outcome was a 3. First outcome was a 2. First outcome was a 1. It wouldn't change the outcome. Okay, so we see that E1 and E2, this getting a sum of 7 is independent of what was your first outcome, whereas getting a sum of 8 depended on what was your first outcome. Is that notion clear?
Yes, ma'am.
Yes, ma'am.
Okay.
Yes, ma'am.
Ma'am, clear.
So if this probability of E is independent of F, probability of E given F was probability of E. That's what we saw. Conditioned, right? Now, if probability of E given F is probability of E, what would probability of E intersection F be? It would be just probability of E into probability of F.
Yes.
Yes, ma'am.
Right. In other words, the probability of the intersection is the product of the probability. So here probability, just as for union, I had probability of E1 union E2 is probability of E1 plus probability of E2 minus probability of E1 intersection E2, right? This was my addition rule. Agreed?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
Now I have a multiplication rule which is talking about the intersection of two events, which is probability of E1 conditioned on E2 into probability of E2. Is this clear?
Yes, ma'am.
In the addition rule, if I had mutually exclusive events, this was going to 0. Probability of the union was the sum of probabilities, right?
Yes,
ma'am.
yes, ma'am.
So if I have independent event, what will happen to probability of E1 conditioned on E2? If E1 and E2 were independent, probability of E1, this would be probability of E1. So in that case, probability of E1 intersection E2 would be just probability of E1 into probability of E2. Agreed?
Yes, ma'am.
Yes, ma'am.
So when I have addition rule, disjoint events, probability of union is sum of probabilities. This is disjoint or mutually exclusive. If I have independent event, probability of intersection is product of probabilities. Probability of E1 into probability of E2. Don't get confused between mutually exclusive events and independent events. Is that clear?
Yes, ma'am.
The multiplication rule applies to probability of intersection. Addition rule is probability of union. Is this clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. So the generalized probability multiplication rule is probability of E1 into probability of E2 given E1 into probability of E3 given E1 intersection E2 and so forth. So from this, I get the independent events. For two events, E and F are independent if the probability of the intersection is the product of the probabilities. Okay. The converse is also true. If the probability, of if E intersection PF is equal to P of E intersection F, they are said to be independent. Note that this is true only for two events. For three events, we have pairwise independence. It is in addition to E intersection F intersection G is probability of E into probability of F into probability of G. We have pairwise independence also. You can refer to the notes. We have talked about pairwise independence for more than two events. Till here, is it clear? Yeah?
Yes,
Ma'am, can you explain how
Yes.
probability of E?
Pardon?
E not F is a probability of E.
Huh? Can you please be louder, please?
Ma'am, she is asking probability of E given F is equals to probability of E. How it is?
See, if probably this one, when occurrence of E happens irrespective of what was your F, then E is independent of F. Probability of E happening. So probability of getting a sum of 7 is independent of whether you had a 4 in the first toss, right? Or 3 in the first toss. It is independent. So it is the same as probability of getting a sum of 7. Understand? So if probability conditioned on F is the same, then when E is independent of F, the conditional probability is same as what we call the marginal probability. Is that clear?
Yes, ma'am.
Okay, so that's how we define independent events. Now, one very important theorem is the Bayes theorem. Let's look at what is Bayes theorem. So if I have a event here and I have two mutually exclusive events here. So first thing is, let me define this using another example which you are going to take. Suppose I have a manufacturing firm which is getting its raw material from three places, A, B, and C. Okay, can I get one unit from A and B, or should I get one unit from, this is getting its parts. Okay, I'm assuming I have a manufacturing firm which is getting its units from A, B, and C. Assume 30% of my items come from A, 30% come from B, 40% come from C. Okay, I think that is 20, 30, and 50. Okay, let me put it the same thing. 20% comes from A, 30% comes from B, and 50% comes from C. Is this clear?
Yes.
Yeah?
Yes, ma'am. Yes, ma'am.
Now, so these are the items. These are the items. These are 100 items. This is coming from A. Now, all that is coming from to me are not good. I have some defective items also. Okay. And what is given to me? It is showing that the percentage of defective items produced by A is 3%, B is 2%, and C is 1%. What does this mean? Percentage of defective from A is how much? 3%. Percentage of defective from B is 2%. Percentage of defective from C is 1%. In other words, I have a defective. This is my defective. Is this clear?
Yes,
Out
ma'am.
of these 100, these are my defective items. Is that clear?
Yes, ma'am.
Yes.
Okay, right. Now, the first thing I want to know is, I jumble up all my units. I pick up one unit. I want to know what is the chance it is defective. This is what I want to know. Is this clear?
Ma'am,
I know.
can you repeat what we...
See, I have, say, 100 things which are coming, 100 same type. So assume that I have 100 bicycles. 20%, 20 is coming from this factory A, 30 is coming from factory B, or cell phones. 20 is coming from factory A, 30 is coming from factory B, 50 is coming from factory C. Is this clear? Okay.
Yes.
Yes, ma'am.
Now all the 20 that are from A, see this A has some defectives. That is 3% of whatever A produces are actually defective. Okay. So that is what is the probability of finding a defective if it comes from A? It is 3%. Is that clear?
Yes, ma'am.
Yes.
Similarly, defective from B is 2%. And defective from C, given it's from C, is 1%. Okay, that is what I have. Till here, is it clear?
Yes, ma'am.
Okay, now I have the 20 items that have come from A, 30 items that have come from B, and 50 items that have come from C. I mix all of them are identical. I mix all of them together. Okay, I pick up one item at random. What is the chance it would be defective? That is the first question that I am asking. Would you all agree that that is the same as probability of the set D which I have drawn there?
1.7%, ma'am.
I'm not asking, let's work it out. So what would that D be? Would you all agree that I can write this set D as D intersection A, union D intersection B, union D intersection C?
Yes, ma'am.
Yes, ma'am.
Yes,
No,
ma'am,
but
we can.
so the probability of D is going to be the probability of these three union.
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Are D intersection A, D intersection B, and D intersection C mutually exclusive?
Yes.
This is my D intersection A.
Yes,
Right?
ma'am.
Yes, ma'am.
This would be my D intersection B. This would be my D intersection C. So can I apply my addition law to write this is D intersection A plus probability of D intersection B plus probability of D intersection C?
Yes, ma'am. We can.
Now, what does my multiplication law say? What is probability of D intersection A given my multiplication law? This is probability of D conditioned on A into probability of A.
Yes, ma'am.
Yes, ma'am.
This is what my multiplication law says, right? Similarly,
ma'am.
so I have a probability of D conditioned on A into probability of A plus probability of D conditioned on B into probability of B. D conditioned on C into probability of C. Agreed?
Yes,
Yes,
So
ma'am.
do I know probability of D conditioned on A?
Yes, ma'am.
Yes,
What is
ma'am.
that?
0.03.
Probability of A?
Probability of A
0.3.
is 0.2.
That is
0.2. Probability of
0.2, right?
0.2.
So this is 0.03 into 0.2.
0.2.
This is 0.02 into 0.3
0.3.
plus 0.01 into 0.5.
Five.
Agreed? So I
Yes,
get
ma'am.
a probability of defective.
Yes, ma'am.
0.017.
Yes.
Okay, is this clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So the probability of any event when it can be expressed. So this A, B and C should be mutually exclusive and collectively exhaustive. Okay. Then this probability of D can be expressed in this way, and this is what we call the law of total probability. Okay. Till here, is it clear? The probability of D is given by this.
Yes, ma'am.
Yeah.
Yes, ma'am.
Okay. Now I pick up. So I picked up an item and I know what is the probability of it being defective. Okay. You're mixing up all these items. Now I'm asking you the question. Given it is a defective item, what is the chance it came from A? What was the prior probability that it came from A? Suppose I just mixed up all the items and picked up an item. What is the chance that that item came from A? What is the probability that that item came from A? Suppose without, it was 0.2. Now I'm giving you additional information. And what is that additional information?
That it came
It is defective.
It is defective.
Now I want you to, so given the information that is defective, so this is very clear to the Monty Hall problem. Probability of you choosing a door first was 1/3, 1/3, 1/3, right? Now
Right.
I'm open a door and I've shown a goat. Now, would you still choose the same door or would you change your choice? So will your probability of finding a car behind door 1 and door 2 be the same given this extra information? So what is this probability of A given D? So this will be again from a definition, probability of A intersection D divided by probability of D. Would you all agree?
Yes, ma'am.
But what is probability of A given D? It is D given A into probability of A. I already computed this, right? This is this term.
Yes.
This is what we refer to as Bayes theorem. Okay. So what is Bayes theorem? The posterior probability. This is what we refer to as posterior probability. A given D. Probability of A was a prior. A given D is the posterior probability, is probability of D given A given by all these terms. So this is what we refer to as the Bayes theorem. Is this clear as to what a Bayes theorem tells? It gives you the posterior probability and the revised probability with extra information. Is this clear, the idea?
Yes, ma'am.
Yes, ma'am. Yes, ma'am. Clear.
Right. So that is about Bayes theorem. Okay. I think we are nearing the end of the session. I'll share these notes and with Prashant. Is Prashant back?
Yes, ma'am. Yeah. I'm there.
Okay. Hi, Prashant. So I'll share these notes. I think if there are no more questions, I'll stop here. You can just look at the notes, which tells you about how to construct probability trees also, and a very simple way of computing your probabilities. Thank you all. Any more questions?
Thank you so much, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you all. Good night. Good night.
Actually, this session will help a lot even in week 8.
Yes, yes, sir.
I do not know what is week 8. Okay. What is week 8?
They had some conditional
This only,
probability is in week 8.
Pardon?
Conditional probability.
Conditional probability.
Conditional
It is
probability,
in
ma'am.
Okay, okay. I think yeah, but Prashant told me to cover that portion of syllabus also, so I did that. Okay.
Yes,
It's
ma'am.
really helpful,
Thank you,
ma'am.
ma'am.
Okay. Right. Thank you.
Because
Thank you all.
thanks a
Yeah.
lot,
Yeah.
ma'am.
Yeah.
Thank you.
Anytime you guys think that it would be helpful, please inform the organizers and the administration. I'd be happy to conduct these sessions. Okay.
Thank you, ma'am.
Yeah.
Thank you.
Okay, ma'am. Thank you.
Okay,
Thank you
ma'am.
all. Yeah.
Thank you,
Okay,
ma'am.
Bye.
Thank you, ma'am.
Bye and good night, everyone. Yeah. Thank you.
Bye.
Bye, bye,
Yes,
ma'am. Good
ma'am.
night.
Bye.
Good night, ma'am.
Good night. Good night.
Right, ma'am.
Hello, Prashant. Are you there?
Yes.
Prashant, I want to know how to use discourse. How I can put questions, doubts in discourse. I haven't go through this yet.
Okay. So, I mean, you are the qualifier student, right?
Yes.
Okay. So, it's not about discourse. So, then have you heard this discussion forum?
Yeah, I heard, but I didn't know how to use it.
Okay. So, do you access of that link? Discussion forum?
I don't know. I don't know about that.
Okay. So, let me check whether it is. So, it's a discussion forum. You can simply post your query there. Let me check where is the link.
Can you show me how to do that? Because I am receiving doubts from other students, but I'm not able to put my doubts on there.
Is there any plus sign? Can you see there plus sign?
In which window?
1 second. Let me open the discourse from website. Just to give me a minute.
Okay.
So, I mean, on the left side, on left top, you can see the new conversation plus sign. It is
Yeah,
on
yeah,
top.
yeah. Yeah, I
So
can see that.
simply you can go there and you can simply write your query.
Okay.
Then
Is there any specific sites for each subject for stats, for maths, and for cities, or all of
yes,
them I
it's
can
a,
paste
no,
here?
no, it's a different. It's a different for every course actually.
Okay. So
Okay, so you can simply check your front end, right? In front end, there will be some general instruction and important link, right? So you can
yes.
go there. There you can find the discussion forum link for every course actually.
Okay, okay. Wait for a second.
Sir, the same problem for me also.
Yeah,
Discussion forum link is there, but if I log in like that, it is coming. If I try to enter my login, it is not at all. I am unable to complete it at all. Once I click my ID, 101 already it is there like that. It is coming and it is not accepting. I don't know. So many times I have sent mail also. Nothing has happened still.
Okay, to support team, right?
Yeah, to support team, I have sent so many times, 3-4 times I have sent. Nothing, no, nothing. I am unable to join that discourse form.
Okay, don't. Okay, so all of you can you write your mail IDs, maybe your registered mail ID in chat box. I will copy and I will talk to team tomorrow morning. What is the problem?
Yes, I'll just write,
Please,
sir.
just
Yes.
please write your registered mail ID, right? Through which
Yes.
you're registering the course. Okay.
Yes.
So where we get the link of notes, sir?
Notes
Notes,
will
sir.
upload in the under supplementary content by tomorrow.
Sir, the
Okay, sir.
same, our IITM ID only is the username. That mail only.
Sorry. No, yeah. The see.
23F, like that only.
The mail ID through which you have registered for your course.
Yeah.
Okay.
Prashant, when we will get the IIT email ID address?
Once you will complete the first term.
Okay. Okay.
Those
Matlab
are my-
after final quiz after April.
Yes. Once you will see, thing is that once you will complete your qualifier courses, right? Say,
Okay.
then I mean, suppose it starts on your completed math one complete. I mean, you are qualified for first term, then you will be the
Yes, sir.
student of this degree. Then next term you will get the student. I mean, IITM mail ID.
Student mail ID. Okay.
Huh.
So,
Yeah.
so can you give access to 14 March session which was taken by TS?
14th March.
Yes, sir.
Okay, sure, sir. We'll give you.
And so extra activities are released on which day? Third activity.
Okay, so second, I think for second peer review is done. I think what's the due date of peer review? Anyone can confirm?
Yes, sir. Yes, sir.
It's
I
over,
completed
right?
my review, sir. What's it?
Okay, so my question is, peer review due date is over or it's still pending?
No, it's today, sir. It's by today.
Okay, today. Yeah, then by tomorrow we'll release the third activity.
Okay, sir.
Okay,
Yeah.
sir.
Yeah. Okay, then I am taking noted down the mail IDs. Okay. So we'll talk to the team and we'll rectify it. Yeah, so I have given the access of the front end also. I'm sorry, that TSS service.
Okay, sir.
Thank you, Prashant.
Okay. Okay, so three of you have doubt regarding this discourse and all, right? I think if you
Yes, sir.
I got the mail IDs, all of this, it's a yesterday domain. I mean, it's IITM domain mail ID.
Yeah.
Then you have been issue maybe then with the discourse, right? Because if you are the term student, then you can post your query on discourse,
Yeah,
right?
like the thing is that I'm not able to understand the discourse over there because, like, where should we pose the question?
So the same thing you can see there.
No,
One
no.
plus.
No, once I click it, it is asking for login, but I'm unable to log in at all. Our ID doesn't work.
Okay,
That
no
is the
problem.
problem
Okay,
I'm
so
facing.
what we'll do, I will cross check with the team. Maybe we'll send to you one right what you can say invitation from the discourse. Okay,
Sir,
then you can.
invitation I got 3 times. All those links are also not working. Same problem with all the invitation. Like that it happens for me. I don't know why.
Okay.
Yes, sir.
Okay.
Same with me.
Okay. So
Yes.
can you tell me the last 3 digit of your roll number? I will write down the problem.
This
Exact
one,
problem.
23F 30101. Kirti Sri
One,
Radha Ram Mohan.
Okay. Okay. So I mean
This
you are
one.
not able to access, right?
I am unable to enter at all. My ID itself,
Okay.
link as I have received so many times. I tried, nothing is working, sir.
Okay. Okay. No problem. I will cross it. Same
Okay,
problem
sir.
with roll number
23F 3854.
854.
Yes.
Okay. Fine. And 221. What's your problem? Can you please? I think hers, right?
It is. It is.
Yeah.
Sir,
So what?
I'm not able to understand the discourse over there. Like where we should pose the question.
Can you see one plus sign on below right corner? It's a
Hello.
blue shaded thing. So simply you can go there and if you click, then you can write.
Right. Okay. And sir, from where we have to do the peer review?
So peer review, once your due date of submission due date will be over, then you can enter your. I mean, then you will be able to do your peer review. Just click on that. Just go under section extra activity where suppose extra activity 1 or 2. Then there will be one peer review section. You can do the peer review from that section. You have to do at least 3 peer review.
Okay.
Okay. Yeah. Okay then. Is
Prashant,
that all
for
right?
peer review, I didn't see any link in my dashboard.
No, it should be there. See, first of all, can you go to?
Yeah, I am in a weekly extra activity tab. which
Mhm.
shows extra activity of for the course, instruction slide for extra activity, and extra activity
No,
1, 2 description.
can you go to the extra activity 2 where submission is there?
Oh, I have to enter it. Extra activity 2 submission. I have click on that.
Just click on that.
After that, wait, it's loading.
Yeah.
Excuse me, sir.
One Ritesh, one second. Or simply
Yeah. I see. Yeah.
yeah, and just prefer that under extra activity description, right? We have provided one slide with you. So you can prefer that one. So it will be helpful to understand the how to do peer review and all.
Okay.
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 So,
Hello.
yes.
Can I speak Hindi?
Yeah, fine, no problem.
मैं जेई लिस्ट का स्टूडेंट हूँ और मुझे अभी तक उसका इनवाइट नहीं मिला है ये
किस
डिस्कोर्स
चीज
वाला
सो आप क्वालिफायर ये फर्स्ट टर्म है क्वालिफायर का या फिर ऑलरेडी
ये
आप
जेई लिस्ट जेई
सॉरी
जेई लिस्ट है मेरा
तो जे
जनवरी
बेस्ड ओके नहीं नहीं, आपको जो मेल आईडी मिली है आपका पर्सनल मेल आईडी है या फिर आईआईटीएम मेल आईडी है
ये आईआईटी वाला है
आईआईटीएम वाला है
हाँ
ठीक है आप मेल आईडी मुझे यहाँ पे जी सॉरी जूम चैट पे पोस्ट कर दीजिए मैं कल चेक करता हूँ एक बार सुबह आई मीन सुबह टीम के साथ ओके आप जी चैट में मेल आईडी आप डाल दीजिए मैं चेक करता हूँ
ठीक है कर रहा हूँ
या
Excuse me, sir.
यस रितेश
So in extra activity 2, I completed my all peer reviews, but there is showing some waiting reviews for myself. Like it is showing it is completed 2 reviews only. So is there any
okay
problem for me?
okay 2 reviews from others right
Yeah.
I mean okay have you done the 3 reviews from your end
Yes, sir.
okay
I had
don't worry
completed
then
4 reviews, sir.
okay no don't worry so it's we'll cross check okay so one more thing let me clarify regarding see the peer after once peer review due date will be over right then you will get some marks so that's not the final marks okay actually after that we are cross checking the data from our end will if there is too much discrepancy and difference in the marks given by the peers right then what we are doing we are cross checking and we are giving the marks from so I mean we are so marks given by from our end will be the
When
final
I'll
mark
get the final marks, sir?
it will take some time I mean some 4 to 5 days at least okay
Okay, sir.
Excuse me, sir.
yes
ये मैं बोल
Sir,
रहा था मैं
sorry
मैं
it is
मैं पहले
permission
भी
to
बोला हूँ
access
yeah one by
email.
one by
Sorry.
okay you can continue
yeah please go ahead
रोशनी go ahead हेलो हाँ
yes
मैं बोल रहा था ना कि मैंने पहले भी बोला हुआ है इसके लिए कि नहीं मैं ऐड नहीं हूँ उसमें ना तो इसमें थोड़ा ध्यान देना मेल भी किया है मैंने बहुत बार बोला हुआ मैंने कॉल करके भी फिर भी नहीं ऐड हुआ हूँ मैं इसमें मतलब
ठीक है
इनवाइट
ठीक
नहीं
है
मिला
ठीक है
मुझे
आप उसका लोड मत कीजिए चेक करता हूँ ठीक है कल तक हो जाएगा ठीक है या यस यस रोशनी
It asks permission to access the Gmail G form, sir. Shall
which
send 5:40 p.m.
which
regarding the gate results.
I'm not sure about that Roshni gate results so it's from team it has been sent out
Yes, sir. Yes, sir. There is some G form to validate that result. But the student who has not completed that, then how can it check, sir?
so it's asking for access right
Yes.
okay then I need to cross it because I'm not sure I mean I was not aware about that G form okay we'll check and if that is the case we'll ask to them so that they will allow to everyone so that everyone can access okay
Okay, thank you,
There
sir.
is written, sir, if you have appeared and received gate result recently in below G form, then click on the form and fill it.
okay maybe uh, due to domain ID I'm not sure I think I need to check actually I was not aware about this gate G form I will check. Okay, don't worry.
Okay, sir.
Yeah. Okay, then I think so. Week 8 is now you will be able to do the questions from week 8, right? I'm hoping because I think ma'am has covered the things already.
Yes, sir.
Okay.
And when will the revision session is, sir?
I think this was the revision session with this revision session from 5 to 8. That's okay. Actually, we had requested to ma'am, so ma'am took this session. Okay. Okay. Okay, then thanks, sir. Okay.
Thank you, sir.
Thank
Thank you,
you.
sir.
Bye. Bye.